Okay, in 7.4, we're going to cover two more applications of antiderivatives. So we've been working with, in 7.2 and 7.3, what are called solids of revolution. And so we're spinning these objects and we're creating a solid object. It's sort of filled in. In this section, we're going to be taking a look, first of all, at surfaces of revolution. That's actually where, it's the other way around. Secondly, at surfaces of revolution. Surfaces of revolution directly connect back to our solids of revolution. They're just the outside shell. So you just get the outside picture of it. So that actually fits more with our description when we're looking at the outside of the soup can only. We're not looking at the inside of the soup can. Or the outside of the bowl only. We're not filling in the bowl with the sand or the pudding or the whatever we're supposed to be filling it in with, okay? The other one is arc length. So arc length is something that we talk about in trig, usually for the first time, where you're finding the length of something that's curved, right? So distance formula can find straight edges for us, right? Like that's not a problem. So things that are straight, cool with a distance formula. Once they get curved, we have a little bit more difficulty. We've got to use some trig to do this. And now we're not going to just use a curve that's very specified, like a circle. We're going to use something that's arbitrary. And so that's where we're starting. All right, so arc length. So we're going to let y equals f of x be a smooth curve on the interval from a to b. Our arc length, either in terms of x or of y, are the same formula. It's the integral from a to b, or c to d, of the square root of 1 plus the derivative of the function that's being squared, dx. So the thing that's going to happen with arc length and also here with surfaces of revolution is that we're not going to have to work nearly as hard to figure out how to create this, the situation and so forth. It's typically given to us. At least enough of it's given to us that we don't have to sort of decide, especially for arc length, am I doing this with respect to x or with respect to y? I'm kind of told which one I'm using, so I don't have to worry so much about getting the orientation of the image right. And so, you give a little, you get a little. This one's actually a pretty good get. We get something that's going to work out easier for us, at least in terms of conceptually setting the thing up and starting. So we're going to take a look at an example. We have y equals x to the 5th over 10 plus 1 over 6x cubed. And our interval is going 2 to 5. And so they give us 2 to 5, which means they're telling us it's going to be in terms of x. Okay? So this is going to be in terms of x. Now, you might notice, and I will write it here on the screen as well, that this formula in terms of x from a to b of the square root of 1 plus f prime of x squared dx actually has a derivative in it. So we are given a function, and the first thing we need to do is we need to find its derivative. So we're going to find f prime of x, or in our case, it's going to be y prime of x. So what is the derivative of x to the 5th over 10? Derivatives, yeah. We're going to be going back and forth. Derivatives and antiderivatives, the same problem. Okay, x to the 4th over 2. All right, so the 5 is going to come down. The 5 is going to reduce with the 10 in the denominator. We're going to be left with a 2. If you want to see more details of it, write the 5 down and you'll see it reduce. The other part, in fact, I'm going to rewrite before I even begin. So this would be 1/6. Don't go moving the 6th. And this is x to the negative 3, right? So what's the derivative? What's the derivative of 1/6 x to the negative 3rd? Okay, so it's going to be a negative. The 3 is going to come down. So it's negative 1/2 x to the negative 4. Okay, so it's caught two of us so far. 3 as well if you count my just change in language, right? Make sure we're doing the derivative or the antiderivative at the right time. And if you want to rewrite this, we certainly can. In fact, I kind of want to because I think it's going to be a little bit cleaner eventually to have it rewritten. My notes, I don't have it rewritten. Let's leave it not rewritten. Let's see how it goes. If you want to rewrite that x to the negative 4 and put it back on the denominator, feel free to do so. Okay, so this is our derivative. We're now ready to do the arc length formula because we have all the pieces at our disposal. So the arc length is defined as a lowercase s. Okay, so that's what we use. S equals r theta is from trig. You might remember that. It's for just the arc of a circle. So we're using the s again here. So our integral goes from 2 to 5 of the square root of 1 plus. And it's this quantity. Now, you might happen to notice there's a 1/2 in both pieces. I'm going to actually write that in front of it. You don't have to do that, but I am. This is x to the 4th and then minus x to the negative 4th. And all of that, including the 1/2, is squared, like so. Okay, is the setup okay? See where all the pieces came from? Feel like you could recreate that more or less if you did a couple of them, have some practice with it, but it makes sense. Okay, so working through this, however, remember you can't just take square roots of individual pieces. That's not a property of square roots. We're going to have to distribute and clean this up underneath the radical before we can move forward. And it's a little bit messy to do, but it's not impossible. It's something that we have the tools to do. We just might have to go back in our brain to think about all the algebra that's going on, right? So this is 1 plus. The 1/2 squared would be 1/4. And then if I do x to the 4th minus x to the negative 4th, I'm multiplying it by itself, right? So when I multiply the first terms together, that's the easy one. That's x to the 8th, right? Add x when it's x to the 8th. What happens in the inner and the outer terms? Well, they're the same. Let me change colors here. So the inner term is negative x to the 4th times x to the negative 4th, right? And the outside one is another one of those. So somebody tell me, what do you get when you multiply x to the 4th and x to the negative 4th? You get x to the 0. What is x to the 0? Well, it just says 1. You're right, it's 1. So this is the quantity 1, and it's really a negative 1 because these are multiplied with a negative, right? So I have negative 1 inside here, and I have negative 1 right here. So when I do my inner and my outer terms, I actually get negative 2. It's a little different. We don't usually see a constant happening in the middle of factoring or multiplying out a factor set. But it is correct. And then we're going to have a negative x to the 4th times negative x to the negative 4th times x to the negative 4th. That's positive, and that will be x to the negative 8th. All right, a little bit of messy algebra. It's not as bad as it could have been, and it cleans up pretty nicely. All right, so taking a look at what remains, what do you notice? Well, I really don't like the 1 to the 4th. I mean, let's be real. That's not real nice. Right? I don't like that 1 to the 4th being underneath there. If I didn't have the 1 to 4th underneath it would be a little bit cleaner. So instead of having it thought that way, I'm going to get a common denominator between this piece and this piece. I'm just going to write that as 4 over 4. So I'm going to rewrite this, and there's more than one way to sort of think about this. This is just one of them. So I can rewrite this as 4 over 4, and then I'm going to combine it at the same time. So this is actually 4 plus, and now I have my x to the 8th minus 2 plus x to the negative 8th, and it's all over 4. Is that okay with everyone? So why might I want to do that? Well, actually because 4 is easy to take a square root of. It's underneath the radical. I can take the square root of 4. It's a constant. What's the square root of 4? It's just 2. So I can actually pull that 2 out from underneath the bottom of the radical, and I can put it out in front. So I can put this 1/2, right? It's pulling a 2 out in the denominator at the front. And now I no longer have the 4 in the denominator under the radical. I do have a 4 plus x to the 8th minus 2 plus x to the negative 8, and I can simplify that sum. What do you notice simplifies? The constants, the 4 and the negative 2, and while it might be tempting to put them at front, I would encourage you to leave them in the middle, and you'll see why shortly. I have an x to the 8th here. That would give me a positive 2 in the middle, and an x to the negative 8 at the end. Okay. Now, this has a radical, and it has something underneath it that's not just a linear term x. U substitution is not going to work very well here. Because if I let what's underneath the radical be u, I don't have a du in this problem. Okay, so u substitution is sort of out. It's not a good choice. Trig, there's no trig involved here, which means algebra simplification is my last resort. And this does simplify with algebra. In fact, if you take a look at what's underneath the radical and you compare it to what we did over here, I didn't write it all out, but it's actually right here. What do you notice when you compare this one to this one? They're almost the same, right? What's the difference? One's a plus 2 and one's a minus 2. Well, where did that minus 2 come from? Look back at our factoring or distributing. It came from the negatives here and here, right? So if those hadn't been negatives and they had been positives, what would I have gotten instead of a negative 2? A positive 2. So this will actually factor using the same details that I had just done. Now, that's very nice if you happen to notice it, but let's say at this point you were like, I didn't notice that. That wouldn't have been helpful to me at this point. Well, what you might notice is that the x to the 8th and the x to the negative 8th at least have a perfect way of being, unsquared, right? Square rooted. So at the very least, I can think, okay, well, this could be written as x to the 4th and x to the 4th, and this as x to the negative 4th and x to the negative 4th. Right? And they have to be linear. They have to have a 1 in front of them. I didn't mean linear. They have to have a constant of 1 in front of them. Otherwise, when I multiply them, I won't get the first term with a 1 in front and the last term with the 1 in the front. And if I'm trying to get that middle term being positive, then the signs would also both need to be positive. And you could check to make sure it works. If I multiply these two together, if I get my sign in there you go. If I multiply these two together, I get 1, right? Or I get x to the 0, which is equal to 1. And the same thing for my outer term. So why is that helpful? Well, it's helpful because it's identical to itself and it's underneath the square root. So whether you want to actually see me write it or not, I will this time. You certainly don't have to. What we really have here is x to the 4th minus x to the negative 4th squared, right? Plus, thank you. Yes, squared. So the square and the square root cancel, right? So this one and this cancel. I'm actually left with 1/2 the integral from 2 to 4 of x to the 4th plus x to the negative 4th dx. And now we're going to integrate. Holy majoli, what did I do? Oh, I changed my numbers along the way. Oh, I changed it way back up at the beginning. Where did I get it wrong? Way back over here. All right, we'll fix it. Thank you. For the record, it was wrong for a long time before you guys caught it. But you did catch it, so that's good. Okay. Get my 5s all in there. I don't know why. I think I wanted 4s because there's 4s everywhere else. Why not have some 4s there too? That's probably why. Okay. What's the antiderivative of x to the 4th? Yeah, x to the 5th divided by 5. And what's the antiderivative of x to the negative 4? Very good. I've got echoing of it on both sides of the room. Good deal. So x to the negative 3 over negative 3. There's a 1/2 in front. And we can clean it up. In fact, we're going to be putting numbers into it, so I probably would do so. You can leave the 1/2 out in front if you want. So I think I'll leave the 1/2 in front. But when I reference the cleaning up, I'm referencing the fact that it would kind of be nice to put that x to the negative 3rd back in the denominator. Your choice on that, but when I evaluate, I like to see positive exponents usually. So this is the power, or not a power 5, but evaluation at 5 and evaluation at 2. So we're going to put the number 5. We don't get to put zeros in this time. Notice that, right? That didn't happen, so that's a little unfriendly. So I have a 1/2. We have x to the 5th, so 5 to the 5th over 5, and then minus 1 over 3 times 5 cubed. And then from here I have a subtraction, and we'll do the same thing with our 2. 2 to the 5th over 5 minus 1 over 3 times 2 cubed. And all of that's times 1/2, which you could have distributed through if you wanted to before we started. That'd be fine too. 5 to the 5th over 5 is awfully large. 5 to the 5th, that is. But it reduces because there's 5 of them on top and there's 1 on bottom. What will 5 to the 5th over 5 become? Anybody know?
25 squared by.
Okay, so it will be 5. Well, we have a 5 in the denominator. So it's 625. And your calculator can do it. I'm not asking you necessarily have to do it by yourself, but there's one of these that's going to cancel. So this is really just 5 to the 4th. 5 to the 4th is 625. So we have 625 minus, over here, 5 cubed would be 125. So this would be 125 times 3. What is 125 times 3? 375. Very good. So we have minus 375. So all of that would be subtracted. 2 to the 5th is 32. 32 over 5. Good. And the denominator, I would have 1 over 3 times 8, so 1 over 24. Okay, that's probably as much as I'm willing to simplify, to be honest, and you don't have to do that last step that I did. Your calculator can number crunch this till the day is done. I mean, it's fine. It's not going to be a very pretty expression when you're done. It's going to be an ugly kind of decimal. It could be a worse decimal, but it's either, if you do it in decimal form, 309.3195, that's its decimal form, or if you do it in fraction form, it's 618,639 over 2,000. There you go. All right. So in practical purposes, right, the decimal expansion makes the most sense because this is something that we would be measuring, right? It's an arc length. This is the length of a curve. So doing it in decimal form is perfectly fine. If the decimal had a repeating version of it or whatever, we would put it for sure back into the radical or the fraction form. And if there happened to be anything with trig where there were some angles and some pies and things like that where it's better, or square roots involved, anything irrational at all, we would want to make sure we leave it in an exact form that way too. Okay, we're going to do one more. Not all of them. Let me mention this first. This was just fantastic right here. This step right here was beautiful. Maybe you didn't realize how beautiful it was, but it's pretty nice. And things do not always actually clean up in such a way that you can take the square root of something that's added together. Agreed? It doesn't always happen. And so there are going to be some examples that look like this, where it says to do this with your calculator. And we all said, yay, that sounds good. I want to use my calculator to do this. And so let's run through how we do that first or next. This is the same as x to the negative 1, right? So every time we work with arc length, we're starting by finding the derivative of the function. So what is the derivative of x to the negative 1? There we go. Negative x to the negative 2. Or if you wish to write it, this is negative 1 over x squared, right? Either of those versions are fine. So if we're finding our arc length, s, it's going to be between the limits of integration it gave us, which is 1 and 3, of the square root of 1 plus, and I don't care which version it is you write this in, so I'm going to write it in, I'll just write it in the first one without the fraction form. When you do this, you do not end up getting something that simplifies itself all out real nice. So this is the square root of 1 plus x to the negative 4. There's no fancy constant that I can manipulate. There's no factoring that I can do. It's not even a trinomial that I could try. It's a binomial. And it's not even a binomial that has like subtraction where like you might look at it and say, is this difference in squares, which wouldn't be helpful in this context, but it still has the ability to factor. This is a sum of something squared, right? It doesn't work like that at all. What that means is your calculator is going to be your buddy. So grab your calculator out. I'm going to remind you how you put this in case you have forgotten, haven't done it in a while. You're going to put in the square root part, everything that's inside of the integral, in your y1, okay? So we're going to write into our y1 the square root of 1 plus x to the negative 4. The square root of all that. There's a couple of ways to do this. I'm going to do it just in my regular screen. Okay, so go back to your regular screen. You have an option that's math 7. Nope, that's not right. 9. I think it's 9. Yeah, math 9. So if you click the math button and choose option number 9, it either says FNINT. Does anybody say that? Okay, Andrews does. If it says FNINT, let me remind you how you put this in. And then I'll tell you everybody else how theirs is working. You're going to tell it y1, comma x, comma, and then the lower limit of integration, which is 1, and the upper limit of integration. We get y1 underneath the vars button. So you hit vars, y vars function y1. Looks like that. And it'll give us a decimal approximation. So let me tell you what my decimal says for this one, and then I'll show you the other version if your calculator is working differently. I have 3 decimals written down. It doesn't tell me how many to go with, so we'll go with 3 for this one. The other option is that when you actually hit that math 9 button, it pulls up a script S, and it has this tiny little box down here, this tiny little box right here. It has a box here, and then it has a D, and then it has a box here. Does everybody else's look like that? Okay, so this is actually really friendly notation. This means your operating system's a newer operating system than the one that Andrew and I have, which is fine. And so you're actually just going to fill it in so that it matches the limits of integration and the pieces that you have. So what you're going to do is you're going to put the 1 down here. You're going to put the 3 up here. You're going to put a dx over there. And if you've stored it in y1, you're going to put y1 here. And let me remind you how you get y1. You get y1, not by hitting y equals, by hitting vars and then y vars and then function, and then there's a y1. That's where the y1's located. The x is the x button on your screen, just like you would use if you were graphing or something like that. Okay, did everybody's calculator give them back expression that says 2.147 and some more? Yes. Okay, so we definitely need to be able to make use of our calculator when we have to. And you could, of course, make use of your calculator to verify the first one we did if you wanted to, right? Absolutely. And in fact, I think it's a good idea. All right, the other thing in this section is surface area. So surfaces of revolution. So again, this is the surface of one of these solids of revolution that we've been doing. So let y equal f of x have a continuous derivative on AB. And notice this says capital S, right? The other one is a lowercase s, which is not the best notation because I don't know about you, but lowercase and capital S's look a lot alike. So try to be really clear about which one you're doing when. And the area of the surface of the solid of revolution. And you'll notice that the formula kind of looks like it's a combination of a couple things we've done. You notice the 2 pi out in front? That's like it was for which formula? Where do we see 2 pi's? Shells, absolutely, cylindrical shells. And then it has the Rx or the Ry, which also looks like the shells, right? But notice what's underneath there, or after the Rx or the Ry. It's the arc length stuff, right? So you've got your square root of 1 plus the derivative of f or y. The derivative of f or g, and then squared. Okay, r is still the distance between the axis of revolution and the graph. Okay, that's the radius, just like it was when we did cylindrical shells. So we do have to draw a little bit on this one just to make sure we get our radius right, as we've drawn on our others. Are you ready to try one? 1 second. Okay. Okay, we're all good. A couple people still writing. Good. Okay. So here's our example. We have a lovely square root graph. Y equals the square root of 9 minus x squared. This is actually a very familiar to you graph. You may not recognize it in its form right now, but it's half of a circle. If we were to square both sides, we'd have y squared equals 9 minus x squared. And if we move the x squared over, this is x squared plus y squared equals 9. So this is the top half of a circle. That's the image this is. I'm not asking that you have to know that, but it is actually a familiar image, just in an unfamiliar form. We're going to graph this, and you're welcome, if you didn't recognize the form, of course, to still use your calculator to do so. But the graph is going to look something like this. With your calculator support or with your own knowledge of circles. It looks something like that. It's not perfectly symmetric, but I think we have the right idea. There is a little bit of a nuance to this. I'm not shading everything underneath it. It says I'm supposed to go from -2 to 2. So when I'm looking at my shading here, I'm going from here to here, and I'm shading in between there. So the graph is right in here shaded. Okay, is that okay? It tells us how it's spinning. What does it say? Yeah, it's spinning around the x-axis. Okay? So we are trying to find the radius, that's that r of x value, and it's going to be taken from wherever we are on the axis of revolution, which ours is the x-axis. So I'm going to just put this orange point here. Sorry, got to get it to be a point here. So I'm going to take this point, and I'm supposed to be finding the distance up to here, right? So how am I going to find the distance, or what would be representative of this orange piece right here from the x-axis up? What is that?
Square root of 9 minus x squared.
Yeah, it's the height y, right? The height y here, and y is represented exactly like David said as the square root of 9 minus x squared. So this is my radius. It's the distance from the x-axis, because that's my spinning axis, right? Out to the curve, wherever it is. That's really all we need this picture for, is to figure out what we're going to get for our radius. Everything else is part of the form that we were asked to use, or the previous slide asked us to use before anyway. All right, so we still need to do the derivative though, right? I need the derivative of 9 minus x squared. And it might be helpful to remember that this is 9 minus x squared to the 1/2. So what is the derivative of this quantity? Okay, does everybody agree? Well done. All right. The 2's are going to cancel, right? This 2 and that 2 are going to reduce themselves. And I'm going to rewrite this and clean it up just a little bit. I'm going to put the negative x on top. And then I have the square root of 9 minus x squared on bottom. That's my derivative. Okay, so let's try and set up our surface of revolution. It is a capital S. It is 2 pi. The integral along the x-axis goes from -2 to 2. It's supposed to be the radius, which is the square root of 9 minus x squared. We already established that. And then this is times the square root of 1 plus the derivative, which was -x over the square root of 9 minus x squared dx. Move it over just a little bit. Okay, so it looks ugly. It actually cleans up pretty nicely as well, kind of like the earlier one we had seen. So take a look at what's going to happen. Here's my 2 pi. Still have my integral -2 to 2. This is the square root of 9 minus x squared. And over here I have another square root, and it's 1 plus x squared over 9 minus x squared. Right? The square and the square root cancel in that squaring process. Okay, is that okay? Now we're going to combine the pieces that are the added pieces underneath that second square root. That's not too bad, because the denominator that it matches with is going to be the other denominator to have. So it'll be 9 minus x squared plus the x squared that's on top over the common denominator of 9 minus x squared.
So the square root 9 minus x squared cancels out?
Yep, there's going to be some canceling going on. You're right. Notice these two pieces. Those add to 0, right? And David already noticed this, but let me make it sure everybody sees it very clearly. I have the square root of 9 on top, or I've got a 9 on top. In fact, I can even write it separately. Let's do that. I have a square root of 9 on top, and I have a square root of 9 minus x squared on bottom.
So our answer is just 3.
Close. It's not quite completed, but what's inside of the integral reduces to that. So these two cancel. Did everybody see that? Make sense of that? What's the square root of 9? It is 3. What's the antiderivative of 3?
3x.
It is 3x. And then I'm doing an antiderivative from 2 to negative 2, or negative 2 to 2. So 2 pi. I have 3 times 2 minus my 2 pi, which is 3 times negative 2. All right, first piece, what does that give me? This is 6 times 2, so this is 12 pi, right? The other half is
3 pi.
more than that. This is multiplication, right? So 6 times, or 3 times negative 2 would be negative 6 times the negative 2. So I'm going to positive and another 12 pi, right? So this is going to give me 24 pi. Now, it's not super obvious because my image went from negative 2 to 2. But pretend for the moment that the image that we shaded in went from negative 3 to 3. You know what the formula is for the area of a circle. What's the formula area of a circle? What is that? Pi r squared. It's pi r squared. What's the radius of the circle? Radius is 3 of this circle, right? Right? Radius is 3. So if we did pi r squared, we could actually find the area of the circle, right? Now, we're finding volume, so this doesn't work exactly, right? And we're doing it from negative 2 to 2, but this seems to be in the realm of what would make sense. It is supposed to be 24 pi. This is one of those places, too, where your calculator is going to spit back out at you an ugly decimal expansion, but it really shouldn't if it knew what irrational numbers are and so forth. So we definitely want to express it as 24 pi and keep things exact. But if you wanted your calculator to verify for you that it matched, you could do that, right? You could do this integration with all the ugliness that it was up at the beginning. You could tell your calculator to give you an answer, it'd give you a decimal approximation, and then when you get to the end of all the beautiful cleaned up part, you could put in 24 pi and you could compare the two decimals. You'll notice there's no written work for this, right? We're just back to doing WebAssign. All right, so I'm going to stop right there.